Okay, so let's start. Okay.
Sir, actually, I wanted to ask a question.
Yeah, go ahead.
Yeah, so I wanted to when we start off with the Riemannian manifold, we know that at each point we have that Riemannian exponential map that takes
Right.
a small ball in a tangent space diffeomorphically to some geodesic ball. So,
Okay.
say since the tangent space is naturally identified with Rn, we have a Lebesgue measure over there. So we can restrict the Lebesgue measure onto that ball in the tangent space. Okay.
Right.
Now
Right.
we can push forward that measure by the diffeomorphism exponential, and we
But be careful, be careful, be careful. On the tangent space, yeah, you have the natural Lebesgue measure. That's true. Yes. Okay. Yes. All right. Yes.
then we can restrict it to the ball in the tangent space, and then push forward that restriction onto the
To
geodesic ball.
right. Right. Yeah.
So my question is that on the other hand, we have the Riemannian measure on the manifold, and we can consider the restriction of that on the geodesic ball. So,
Right.
I mean, are they related, like up to some constant or something, or?
No, they're absolutely continuous, mutually absolutely continuous. And in fact, the Radon-Nikodym derivative is given by the Jacobian of the exponential map, right? So,
Right.
so the Jacobian of the exponential map is not, I mean, it's not one. It's a function. It's a function, which depends on the curvature of the manifold. So we'll calculate the Jacobian. I mean, for some cases, for Hn, we can calculate the Jacobian and so on. And we'll give upper and lower bounds on the Jacobian, given upper and lower bounds on the curvature. So, yeah. So, right. I mean, so we'll come to this later in the course. So, one second. See, you have say a ball in the tangent space. Okay.
Okay.
This is 0. And you have x sub p. This is a ball in TPM. And TPM is an inner product space. So you can think of TPM as a Riemannian manifold, right? Itself.
Yes.
Which is isometric to Rn. Yeah. And now the exponential map is mapping to a ball around P. So suppose I take a vector V here. And I look at its image. So let me call that Q. So Q is XP of V. Okay. And so here we have, let's say, the Lebesgue measure lambda P is the natural Lebesgue measure on TPM. All right. So this is when you identify TPM isometrically with Rn, you take the Lebesgue measure on Rn and push it forward to TPM. All right.
Right.
Okay. So you get the lambda P here. And here you have, say, the Riemannian volume measure, dvol. Okay. Now, what is the Radon-Nikodym derivative? So let me call this measure mu. Okay, dvol is mu, say. So I want to calculate the Radon-Nikodym derivative, d mu, d. So let me call the exponential map f. Okay. So yeah, so what is d mu d f star lambda? Let me just call this lambda. So what is this at the point Q? This is a function on this ball. So let me call this ball B0 and this is a ball B1 in M, right? So Q belongs to B1, V belongs to B0. Right, so what is this? So this is going to be the limit epsilon tends to 0 of mu of a ball of radius epsilon around Q divided by so f star lambda of the same ball, right? Okay, right?
Yes.
This ball, you are taking the metric ball.
Yeah, I mean, actually, it doesn't matter. You can take any nice set; it'll give the right thing for almost every Q by Lebesgue differentiation theorem. You just have you need a nice set, nice collection of shrinking sets. So yeah, it doesn't matter really what the. So look, I can compute this on the right hand side, or I can compute it on the left hand side also. So so this is also the limit epsilon tend to 0 of so yeah, mu of f of a ball around V of radius epsilon divided by lambda of a ball of radius epsilon around V. And right, okay. So how do we calculate this? So actually, instead of a ball, I could also take a cube around V. Okay. So what's a good way to do this? So you see, by the Gauss lemma, if I take the line passing through V and I take its orthogonal complement, then the line passing through V goes to the geodesic passing through Q. And the orthogonal complement under the derivative goes to the orthogonal complement, right?
Yes.
Yes.
Okay. And along this, so basically, what I can do is I can take a cube here in the tangent space, which is parallel to these directions. So the line through V and the orthogonal complement, right? So I choose a orthonormal basis where the first vector is V divided by norm V, and the others are a basis of the orthogonal complement of V, right? And I can look at its image under the exponential. Yeah, so I'll get a small cube here, a curved cube, right? And so, yeah, so Right. So how do I want to say this? It's very simple. Basically, see, on the infinitesimally, what do I have? I have some well, it won't be a cube, it will be a parallelepiped. So if I take a vector of length 1 in the direction of v, that goes to a vector of length 1 at q. So this is a vector of length 1. And then, you know, by the Cartan decomposition of the derivative of the exponential, if I look at the derivative of the exponential restricted to the orthogonal complement of v here, then I can choose a basis of the orthogonal complement which maps to an orthogonal set here, right? It maps to an orthogonal set here, right? So, you know, if I take a linear map T, then I look at T star T. And if I take eigenvectors for T star T, this is symmetric. So it has a basis of an orthonormal basis of eigenvectors, right? So that means that T of EI and T of EJ, this inner product will be the same as the inner product of T star T EI EJ, and this will be inner product of lambda I EI EJ. So this is 0 if I not equal to j, right? Yeah.
Yes.
Yes, yes.
So that means the vectors TEI are orthogonal to each other, right? Okay, so I have this one vector which is going vertically, and the other vectors are my TEI. Okay, right? Okay, so now
Yes.
what is the Riemannian volume of this? The Riemannian volume will be basically the products of the sides, right? So it will be 1 into norm T 1 TE2 up to TEN. Okay. T is equal to the derivative of xp at v restricted to v perp. Okay. So this is the numerator here, mu. Okay. And this divided by 1. Okay. So this is my Radon-Nikodym derivative, you see. And so this is d mu d f star lambda at q. So if I square this, then I'll get these squared, right? Okay. So what will the square be? So this will become norm of TEI squared. So product I goes from 2 to n. So that's inner product TEI, TEI. That's the same as the inner product T star T EI, EI, which is the same as the product lambda I, right? Yes?
Yes, yes.
Yes.
And that's basically the determinant of T star T, right?
Yes.
Which is
The square of the minor
determinant of T squared. And the determinant of T is the same So T is the restriction to the orthogonal complement, but in the direction of V, the exponential maps a unit vector to a unit vector. So the determinant of the exponential on the whole tangent space at V is the same as the determinant of T. So this is just determinant of dxp v whole squared. Is this okay? So then I take square roots, and so I get that this thing is equal to the Jacobian, the determinant of the derivative of the exponential at V. Okay?
Yes.
That's it. So that's the Jacobian. So this is not a constant. This is equal to 1 when V is 0, because the derivative at the origin is the identity, but otherwise it's not a constant function. All right. So is this okay?
Yes, sir. Yes.
Yeah. Okay. Orkujit, is this okay?
Yes, sir. Yes.
Yeah. So okay. All right. So yeah. So let me come back to basics. So we were talking about tangent spaces, and so vector fields we talked about, and the Lie bracket of vector fields. So vector fields were identified with derivations of C infinity M. And here you have a Lie bracket. So derivations of any algebra is a Lie algebra, okay, with a Lie bracket, right? That's clear. That's a purely algebraic thing. Yes? Okay. So using this isomorphism, you can transfer this Lie bracket here to a Lie bracket on chi n. Okay. Is this clear?
Yes.
Yeah. And this Lie algebra, of course, this is an infinite dimensional Lie algebra. Morally speaking, this is, I'm putting this in inverted commas because this is morally, it's an infinite dimensional Lie algebra. Well, so it doesn't correspond to a Lie group as such. I mean, it should correspond to some infinite dimensional Lie group, but in infinite dimensions, the correspondence between Lie algebras and Lie groups is not so nice. So morally speaking, this is the Lie algebra of the group of diffeomorphisms. So C infinity diffeomorphisms of M. Lie of this. Yeah. So this is the Lie algebra of this. Well, I mean, morally speaking, okay, this is not a precise statement. So you only have sort of local, I mean, a curve here in diff. So if this is script G and this is capital G, yeah, then a one parameter subgroup here, phi t, a one parameter subgroup of diffeomorphisms. Okay. This will give you an element of the Lie algebra, X. What is XP? It's just ddt at t equal to 0 of phi t of p, right? Okay. And the converse we don't have in full generality. That's why I'm saying this correspondence is not so nice as it is in finite dimensions. The converse is you have a vector field X and you look at its flow, phi t equal to flow of X. So that gives a one parameter subgroup. The only problem is, well, X may not be a complete vector field. So in that case, the flow is only locally defined and so on, and not defined for all times. And so there are these problems there. You get a local flow. So if M is a compact manifold without boundary, then any vector field is complete. So then you do get a correspondence here. Yeah, you do get a one-to-one correspondence between vector fields and one parameter subgroups of diff M. Does this make sense? Is this okay?
Sir, here we have considered the group of all C-infinity diffeomorphisms on M, and then considered it.
Yeah, so that's it's a Fréchet Lie group. It's not a nice Lie group.
Oh, achha.
It's Fréchet, yeah, it's a Fréchet structure. You don't have any Banach structure on it, yeah.
Oh, achha.
Yeah, there's no Banach structure on it, yeah.
I want to,
It's
yeah.
a nasty group. It's
I
not a
want,
nice
I wanted to ask that, like, we are considered, say, AM is a Riemannian manifold. Okay,
Yeah.
then, so it's a finite dimensional Riemannian manifold. Then instead of this group, if we consider its isometric group, then it's always a finite dimensional Lie group, right?
That is a finite
Dimensional
dimensional
Lie
correct.
group. So that's, so like, in here, I mean, what I wanted to say is that here AM is just a Riemannian manifold, right? Instead
So
of,
M is a smooth manifold.
now, when I want to make sense of, say, isometries, etc., I take into account the
Then you
Riemannian
take a Riemannian, fine. You
structure.
take
Yeah.
a Riemannian manifold.
So
right.
when say like it's just a Riemannian manifold, and we look at its isometric group, it's a finite dimensional Lie group. We consider it Lie algebra. Then do we have this sort of some like abstract correspondence to the like in some sense differential operators, etc.? I mean, like here we are having some abstract correspondence, which seems very difficult, but like my group is rather well behaving. So how does that isometry come into the sense of like vector field which like preserve certain things?
Oh, the vector fields are called killing vector fields. So inside diff, so okay, fine. So you have diff M. So inside this, you've got the subgroup isom M. Okay. So of course, this is infinite dimensional, but you've got this finite dimensional genuine Lie group sitting inside. So it's a Lie subgroup. Okay. Right. And this corresponds to the Lie algebra. So here you have chi-m, and here you have a Lie subalgebra of what's called killing vector fields. So I don't know if there's a notation for the space of killing vector fields. So yeah. So there's a correspondence here. So this will be a Lie subalgebra. This is finite dimensional. So a vector field is a killing vector field. Equivalently, that means its flow is a flow of isometries. So that means that inner product of d phi t, if phi t is the flow of x, so d phi t say y d phi t z is equal to inner product yz. Okay. So so to get the killing equation, how do you do this? You have to differentiate this at time t equal to 0, right? So you get that 0 is equal to ddt at t equal to 0 of inner product d phi t y d phi t z Okay. And what is this going to be? So this is going to be inner product of capital D del T covariant derivative of d phi ty. So, okay, I can just take yy because it's determined by its values on the diagonal. So let me just take yy. Okay, so, all right, fine. Okay, I'll stick to yz. It's okay, fine. So yz. Okay, so z plus y d del d dt t equal to 0 d phi t z, right? Yeah. Okay.
Yes.
Now, okay. Ooh. So yeah. So what is d phi t y? What is d phi t of y? So basically, so I have a point P.
It's a covariant derivative, right? Along.
No. But what is this d phi t of y? D phi t is the derivative of the flow, right? I want to say the flows are the flow maps of the flow are isometries. So that's this condition, right? So let me first compute d phi t of y. Okay. So suppose this is y, and I take let's say an integral curve of y, right? So then if say gamma is an integral curve of y, say gamma of s, okay. All right. This is integral curve of y. So d phi t of y at P, right? What is this going to be? This is going to be dds at s equal to 0 of phi t of gamma s, right?
Yes.
Here's P, here's phi t. This point is phi t of P, right? And this curve is, say, this is phi t of gamma. Okay, this curve is gamma. Okay, so this tangent vector will be, if this is y here, this tangent vector here will be d phi t of y, right? Okay.
Yes.
Okay. So now what is this covariant derivative here? D del d dt at, well, I'll make it d del t at t equal to 0 of del s at s equal to 0 of phi t of gamma s. Okay, what is this? So this is by symmetry of the connection. This is d del s at s equal to 0, right? Of del t at t equal to 0 of phi t of gamma s, right?
Yes.
Okay. Now, what is del t at t equal to 0 of phi t of gamma s? That will be x at gamma s, right? The derivative of the flow gives me x. Phi t is the flow of x, right? So
Yes.
this will be x at gamma s. Okay. Now, what is the covariant derivative of x along gamma s? It's going to be the derivative of gamma prime 0 is y. So this is going to be nabla sub y x, right?
Yes.
Okay, at P. All right. So this, what does this become? This, so therefore we get that 0 is equal to ddt at t equal to 0 of inner product d phi t y d phi t z, and this is equal to inner product nabla y x z plus inner product y nabla z x. Right? So this is 0. Okay. All right. So this equal to 0. This is the killing equation. Okay, and a vector field which satisfies this equation is called a killing vector field. Is that clear?
Yes.
So this is obviously linear in X, right? So X is a killing vector field. So the killing vector fields form a vector space, right?
Yes.
And then you have to show that they form a finite dimensional vector space, and the bracket of killing vector fields is also killing. So yeah. Right. So I'll have to think about that. Yeah. But the answer should be, yeah, the vector fields corresponding to the isometry group are the killing vector fields. Okay.
Okay, sir.
Yeah, so I have to think about why they're closed under bracket. I have to think about that a bit. I'm not sure right now. But you understand that, you see, a one parameter subgroup phi t in isom M so this picture is inside isom M, right? This is the identity. When you differentiate it, when you take this x equal to ddt at t equal to 0 of phi t, what this will give you is a killing vector field. All right, that's what we've just shown. Yes?
Yes.
Is it clear? Right. Okay. So, I mean, this should be the so what is the Lie algebra of isom M? It's going to be the set of derivatives of all I mean, it's the tangent space at the identity, right? Which is nothing but the set of derivatives of one parameter subgroups passing through the identity, right?
Yes.
So that will give you the killing vector fields. So yeah, that's. Is this okay? Yeah.
Yes. Yes.
Right. Yeah. So for isometries, yeah, you get nice finite dimensional Lie groups and so on. Yeah. Okay. All right. Okay, so I wanted to talk about, I mean, just more basic things, since we're just doing preliminaries now. So, derivatives of smooth functions, and maps. So M is just a smooth manifold now. So if I take U is an open subset of M, and F is a smooth function on U, then for any point P in U, I can define dFP, the derivative of f at P. This I can define as a linear map from the tangent space TPM to R. So it's a linear functional. Okay. So how is this defined? Well, you take a tangent vector V. So remember what a tangent vector was? It was a linear map on the space of germs of smooth functions at P, which satisfied the Leibniz rule at P. So V, any tangent vector, therefore, will act on a function f defined near P. And so I can just let V go to V of f. Right? So this will define, this is linear in V. So this will define a linear map from a linear function on TPM, right? Okay. So the derivative in this case of a smooth function is a linear functional, an element of the dual. So the dual I'll denote TP by TP star m. Okay, this is also called the cotangent space. All right. And so, for example, if I take a chart phi equal to x1 to xn is a chart on U. Then each xi is a C infinity function on U. And so I can look at dxi, right, at P. This will be a linear functional on the tangent space. Now I can apply this to the basis vectors del del xj at P, right? Yes. So what will this be? This will just be, by definition, it's del del xj acting on the function xi, right? So this will be del del xj acting on xi. And that is delta ij, right? Yes?
Yes,
Yes,
sir.
sir.
So what does that mean? That means that dx1 to xn at P, this is the dual basis to the basis del del x1 to del del xn, right? Yes?
Yes, sir.
Okay. So if I take any vector V equal to summation ai del del xi, then the coefficients ai are nothing but the elements of the dual basis acting on V, right? Okay. Okay, let me stop here. We've got less than a minute. We'll start another meeting. Okay. Okay. So, right. So if I have a chart phi with the coordinate functions x1 to xn, then the xi's are smooth functions on U. So I can look at dxi's. So these will be linear functions on the tangent space. And dxi of del del xj turns out to be delta ij. So therefore, dx1 to dxn at P is the dual basis to del del x1 del del xn at P. And so if I take a vector V in TPM, then the coefficients are just the elements of the dual basis applied to V, right? Yeah.
Yes, yes. Right.
So therefore, what is DFP if f is a function? So this is a vector in TPM. So what is DFP of V? This is going to be V of f. So this is going to be some dxi of V, del xi of f, right? At P. Yes?
Yes, sir.
So what does that mean? That means that DFP is nothing but summation del f del xi at P into dxi, because these take the same value on every vector V, right?
Yes.
Okay. So this is the, I mean, classical formula from calculus, which you used to maybe write in class 10 or 11, right? I don't know, or 12 maybe, I don't know. Or physics, in physics you used to write this. At least I remember writing this formula in school. So anyway, okay. So, well, so we have this same formula on a manifold. Is this okay?
Yes, sir.
Yes.
Right? Okay. Okay, so the derivative of a function you can write in terms of the dxi's. Okay. All right. Now, what about derivative of a map between manifolds? So, if I have two manifolds and I have a smooth map between them, say this is P and this image of P is Q. This map is, say, phi from M to N. Then what is the natural thing to expect? The derivative of phi should be a linear map from the tangent space at P to the tangent space at Q, right?
Yes.
So how do we get this linear map? Well, if you think geometrically, it's quite obvious. If you think in terms of the geometric tangent space, which was given by tangent vectors of curves. So if you take curves passing through P, they go under phi to curves passing through Q. And so therefore they define a tangent vector at Q, right? Okay. But we're working with the algebraic definition of tangent space. So for the algebraic definition, we have to take germs of smooth functions, say G, in a neighborhood of Q. So this is a germ at Q. Here Q is f of P, phi of P. So if I have a germ near Q, what I can do is I can compose it with phi, right? And then I'll get a germ near P. So that gives me G composed with phi. So this is a germ near P. But now if I take a germ near P, I can act on this by a tangent vector at P, right? Okay. So that will therefore give me a map d phi P from the tangent space at P to the tangent space at Q. What do? I take a vector V and then a tangent vector V at Q. This is going to give me a linear functional W. So what W does is it takes a germ G at Q and it maps it to V of G composed with phi. Does this make sense?
Yes.
So this will become, this W will be an element of TQN. It's easy to see this also satisfies the Leibniz rule because V satisfies the Leibniz rule. All right. And this is clearly linear in V, right? It's linear in V. So this is a linear map between tangent spaces. All right. Okay.
Yes.
And if I have a composition of maps between manifolds, then I get the chain rule holds for their derivatives. This is just algebra. It's very easy to verify this, that D of psi composed phi at P is equal to D psi at phi of P composed with D phi at P. Okay, so this will be a linear map from TPM to T phi Pn to T psi phi P Q. Is this okay? Yeah. So you have this chain rule, all right?
Yes.
And if I have a diffeomorphism from M to N, say what is a diffeomorphism? It's a smooth map with a smooth inverse. So I have an inverse, say psi from N to M. Okay. This is the inverse. This is, well, a smooth inverse. So then by the chain rule, D psi at phi of P composed with D phi at P. This will be the derivative of psi composed with phi at P, which is the derivative of the identity. And the derivative of the identity is easily seen to be just the identity of the tangent space, TPL. Right? Okay. So that means that the for a diffeomorphism, its derivative will be an isomorphism at each point, right? Okay. So d phi P is an isomorphism for all P and M. Okay. Yeah.
Yes.
And the inverse function theorem gives a partial converse. That if d phi P is an isomorphism, then phi is a diffeo in a neighborhood of P. All right. Okay. Is this all right? Any question?
That's fine.
It's fine. Yeah. All right. Okay. So we've got derivatives of smooth maps. So the next thing is, I want to talk about the Lie derivative of a vector field with respect to another vector field. So for that, it's good to talk about push forward and pull back. Of vector fields. So first of all, this we can only do if we have a diffeomorphism. Okay, so suppose phi from M to N is a diffeomorphism. Okay, so if I take a vector field, so let me first say what is the push forward. So the push forward is the following. Any vector field on M, I can push forward to a vector field on N. Okay. So how do I do that? Well, I have phi and I have a vector field X on M. I want to push it forward to a vector field Y equal to phi lower star X. This will be a vector field on N. So what I do is, given a point Q in N, since phi is a diffeomorphism, Q has a unique preimage, P, right? So P is equal to phi inverse Q. And then at P, I have a tangent vector, X at P. And now at the point P, I have the derivative of phi, d phi at P. So that will map tangent vectors at P to tangent vectors at Q, right? So I define here Y at Q is defined to be d phi at P of X at P, where P is equal to phi inverse Q. Is this clear?
Yes.
Okay. So that will define the push forward of a vector field. All right. Any question about this? Yeah, I mean, so for example, if I take phi equal to stereographic projection, from R2 to S2 minus the North Pole, then if I take the radial vector field here, okay, so X at P is equal to P itself, this radial vector field. Then under phi, what vector field does this push forward to on the sphere? What will the vector field look like under on the sphere? So here X of P is equal to P. This is the radial vector field. On R2.
Would it look like all those, I mean, longitudes are those that join North Pole to South Pole, right? Those are the longitudes.
Exactly.
Moving towards the North Pole. That is
exactly. So 0 goes to the South Pole. And so the vector field will point from the South Pole to the North Pole along longitudes, right?
Yes.
Basically, what happens is under the push forward, phi is going to map integral curves of x to integral curves of y, the push forward, right?
Yes.
And
Yes.
here the integral curves are straight lines through the origin. So those go to longitudes from the South Pole to the North Pole. And so therefore, the integral curves on the right-hand side will be longitudes, right? So you'll get this longitudinal vector field. That will be the push forward. Is it clear?
Yes.
Yes, sir.
Yeah, so y is phi star x equal to longitudinal. Vectors. Okay. So pullback is just you do the same thing in the opposite direction. So now I have a vector field on n, and I have a point P here in M. And so X I want to define to be, so phi upper star, the pullback, phi upper star of Y. So here, this is going to be a vector field on M. So what do? I take P, I map it across by phi to Q, which is f of P, phi of P. And then here I look at the tangent vector Y at Q. But now because phi is a diffeomorphism, its derivative d phi at P is an isomorphism. Therefore, I can apply the inverse of d phi at P to this vector Y at Q to get a vector X at P, right? So here my X at P is defined to be d phi P inverse of Y at phi of P. Is this clear?
Yes.
Okay. So be careful. I mean, for pullback and push forward, you need diffeomorphisms. You can't do it with smooth maps. So you can't do it in general with just smooth maps. You can't. Because, I mean, for example, for push forward, right? We had to take a pre-image, right? So if the phi is not 1-to-1, then there'll be multiple pre-images. At those multiple pre-images, I'll have different tangent vectors x, and the images under the derivative of phi at different points, they may not give me the same tangent vector at Q on the right-hand side, right? You see what I mean? Yeah, so you can't push forward in general by a map which is not 1-to-1. Okay. Now,
So for
yeah,
we have some relaxation, right? I mean, I can just take phi such that d phi is isomorphism for each. That is right?
that then I can pull back. But I may not be able to push forward, right?
Yes, I can't push forward, but pull back.
Yeah. So okay. So maybe I should clarify. So push forward. This works for diffeomorphisms. Okay. And pull back. This works for local diffeomorphisms, a more general class. Okay, because for local diffeomorphisms, I know that d phi at P is a isomorphism, so I can take its inverse applied to Y at phi of P, right?
Yes.
Yes.
Okay, all right. Now what I want to talk about is related vector fields. So this is a case where push forward works even if the map is not a diffeomorphism. So let me just give you an example first, and then I'll give you the definition. So example is, you take, for example, the cylinder, okay, S1 cross R, all right? So and this is your manifold N, and your manifold N is just S1, and your map phi is the projection, okay, onto the first coordinate, all right? Yes?
Yes.
Now suppose I take this vector field, which is just the horizontal vector field on the cylinder, all right? I just take this horizontal vector field on the cylinder. Then this vector field I can push forward under phi, because how will I push forward? So what I need to do is I take a point Q below, then I look at any preimage of it, right? Now it's going to have infinitely many preimages. The preimages will all look like this, right? Along a vertical line. Yes? Okay. Now I take any of the tangent vectors at any of these preimages. Under d phi, they will all map to the same vector below, right? Yes?
Yes.
Yes, sir.
Therefore, the push forward makes sense in this case, all right? Okay. So I get a vector field y below. So I have my vector field above, and I have a vector field below. And so I have here x in chi m and y in chi n. And what is the relation between these two vector fields? If I take any point P above and I map it by phi to Q, which is phi of P, okay, then y at the point phi of P is equal to d phi at P of x of P. Right? This is true for all P in N. Yeah, is this clear?
Yes.
Yes,
Okay.
sir.
So this is the definition of the two vector fields x and y being phi related. So if this occurs, we say x, y are phi related. Okay, and we write this as x sim phi y. All right. Okay. Yeah, is the definition clear? So in this case, the idea is, you see, what will happen here when I have two phi related vector fields, you can see from the picture, phi is going to map integral curves of x to integral curves of y, right?
Yes.
Yes, right. So, see, suppose gamma is an integral curve of x, right? So let me look at phi composed gamma. Okay, so let's look at ddt of phi composed gamma of t, right? So this is going to be what? This is going to be d phi at gamma t of gamma prime t. Okay, so I didn't prove one small thing, that derivatives map, the derivative of a smooth map, it maps tangent vectors of curves to tangent vectors of the image curves. So yeah, okay, so maybe I should do this. So okay. So I have a smooth map between manifolds phi from M to N, and I want to look at ddt of phi of gamma t. So this is supposed to be an element of the tangent space at phi of gamma t. Okay, so this is how does this act on a germ, say G? This by definition is ddt of G of phi composed with gamma, right? Yes. Okay, G belongs to,
Yes.
this is a germ at N at the point phi of gamma t. Right, this is the definition of tangent vector to a curve. This is how it acts on functions, right?
Yes.
Okay. Now, what is this? This is ddt of G composed with phi, the whole thing composed with gamma, right? So this is what? This is gamma prime t acting on G composed with phi, right? By definition of gamma prime, right? So here G composed phi, this is a germ at gamma t. Yes? And gamma prime acting on G composed phi, this by definition is the derivative of phi, d phi at gamma t acting on gamma prime t acting on G, right? By definition of the derivative of a map between manifolds. Yes?
Yes.
Yes,
Right,
sir.
remember the definition of derivative. Yeah, you let the vector v act on G composed with phi. So the vector v here is gamma prime. The vector v here is gamma prime. You're letting it act on G composed with phi. That's the same thing as applying d phi to the vector v and then acting on G, right? By definition. Okay. So therefore, this proves that ddt of phi composed gamma is d phi at gamma t acting on gamma prime. Is this okay?
Yes.
Okay. So now let's come back here. So if I take an integral curve of x and y is phi related to x, then what do I get? I get that ddt of phi composed with gamma of t, this is d phi at gamma t applied to gamma prime of t. Now, gamma is an integral curve of x. That means that gamma prime t is equal to x at the point gamma t, right? But now x and y are phi related. So therefore, d phi at gamma t applied to x at gamma t, this is the same thing as y at the point phi of gamma t, right? Because x is phi related to y. Yes?
Yes.
Yes.
So this implies what? This implies that phi composed with gamma is an integral curve of y, right? Yeah, it satisfies the differential equation for y, right? Is
Yes,
this
sir.
clear? Right? So that's it. Okay, so when two vector fields are phi related, then integral curves of x go to integral curves of y. So what this also means is that in terms of the flows, so if I look at the flows, okay, wait, let me draw you a picture first. So in terms of the flows, what does this mean? So see, suppose these are the integral curves of x. Okay. Then okay, let me just draw one integral curve. Let me remove the others to make the picture less cluttered. So an integral curve above is going to an integral curve below. Now, what happens if I take P and I flow under the flow of X, right? So I take the integral curve passing through P. Then this point will be, say, phi t x. So let me call the flow of x phi t super x of P, right? Now this goes under phi to what? This goes to q equal to phi of P. And this integral curve, this maps to the integral curve passing through Q, right? So therefore, this point here, the image of this point will be the same as flowing Q under Y. So this will be phi t y of Q, right? So what does that mean? That means that this diagram commutes here, right? That on top I have the flow of x, and below I have the flow of y. And so I get this commutative diagram, phi t x above and phi t y below. And along the vertical arrows, I have phi and phi. Does this make sense? This diagram commutes, right?
Yes.
Yeah, in words, I mean, flowing by x and then applying phi is the same as first applying phi and then flowing by y, right? Yeah, you can see that in the cylinder picture, right? If I flow above first and then project, it's the same as projecting and then flowing, right?
Yes.
Okay. So, in terms of, so if I write out this equation, what does this give me? It gives me phi composed with phi tx is equal to phi ty composed with phi, right? Okay. Now, if phi was a diffeomorphism, then I can take this phi to the other side and I get that phi composed with phi t x composed with phi inverse is equal to phi t y. In other words, the flows are conjugate, right? via phi. Okay. Right? Phi tx, phi inverse equal to phi ty. So phi conjugates the flows. All right. If phi is a diffeomorphism, but in general, phi could be something like a projection from the cylinder to the circle. So then, in the general case, we just call phi a semi-conjugacy. Okay, so it's not a conjugacy between the flows because it's not invertible, but it's a semi-conjugacy. So in other words, you can think of the action below as a quotient of the action above, right? Okay, so phi acts like a quotient mapping between the two the dynamics above and the dynamics below. All right. Does this make sense? Yeah.
Yes, sir.
Okay. So it's so yeah. So in this category, it's of dynamical systems. It would be a quotient mapping. It would take so the dynamics below is a quotient of the dynamics above. Okay, so they're semi-conjugate. All right. The flows are semi-conjugate. Okay. Okay. So what do I want to say now?
So let's start a new meeting.
Yeah, we just have 1 minute. So let me stop this and we'll start a new meeting. Okay, fine. All right. Okay, so, all right. So now let me come back to the notes now, actually. Okay, so we've talked about push forward, pull back, and phi related vector fields. And yeah, so here's this proposition I won't prove, but this is, we've proved one of the implications here. But anyway, so the following are equivalent. X is F related to Y. F semi-conjugates the flow of X to the flow of Y. So F composed with the flow of X is equal to the flow of Y composed with F. And the third property is whenever phi is a smooth function on N, then X of phi composed F is equal to Y applied to phi composed with F. Okay. So I won't prove this, but we can assume this. And the property that we need is that if two vector fields are F, if I have two pairs of vector fields, say x1, x2 on N and y1, y2 on N, so such that x1 is F related to y1 and x2 is F related to y2, then the bracket of x1 and x2 is F related to the bracket of y1 and y2. Okay. So this is just a simple computation using property 3. All right. You use property 3 and the definition of the bracket applied to a function, right? So bracket x1, x2 applied to phi composed with F is going to be x1, x2 applied to phi composed with F minus x2, x1 applied to phi composed with F. And then you use this property 3. So since x2 is F related to y2, x2 of phi composed F, I can write as y2 phi composed with F. And similarly, x1 of phi composed with F, I can write as y1 phi composed with F. And then I apply the property 3 again. So x1 of this function composed with F will be y1 of that function. So that is y1, y2 F, then composed with F. Similarly, minus y2, y1, phi composed with f. And this will be equal to the bracket of y1, y2 applied to phi composed with f. Okay. Is this all right? This is just a simple computation.
Yes.
Okay. Fine. So now let me come to the Lie derivative of a vector field. Okay. So suppose x, y are vector fields on the same manifold M, and phi t is the local flow of x. Okay. Then I can define a derivative of y with respect to x as follows. So you see, in general, if I have two vector fields on a manifold, it's not immediately clear what it means to differentiate one in the direction of the other, because, well, you might say, okay, I take a point P, I want to differentiate y in the direction of x. So how do I move in the direction of x? I take the integral curve of x passing through P, right? So this point would be phi t of P, phi t equal to local flow of x. And then, well, so this is y at P. And then this is y at phi t of P. Okay. Now I want to differentiate, right? So, I mean, naively, what I would try to do is take this vector minus this vector divided by t and let t tend to 0. What is the problem with that?
They live in different tangent spaces.
Exactly. They live in different tangent spaces, right? This lives in the tangent space at P. This lives in the tangent space at phi t of P. How can I subtract them, right? I can't take their difference. Instead, what can I do? What I want is then some way to identify these two tangent spaces, right? I want some way to identify these two tangent spaces. Then under the identification, I can get two vectors in the same tangent space and then take their difference and then let t tend to 0, right? So is there a natural map which identifies the tangent space at P with the tangent space at phi t of P?
Yes.
What is the
d phi t inverse?
right? Exactly. So if I take the derivative of the flow d phi t at P, so this goes from where? This goes from the tangent space at P to the tangent space at phi t of P. Okay. And the point is phi t, the elements of the flow are local diffeomorphisms, right? I mean, they're diffeomorphisms. So this map is an isomorphism, right? Therefore, if I want a vector at P, what I can do is now I take d phi t at P inverse of y at phi t of P. Now this belongs to the tangent space at P, right? Yes. So therefore I can subtract y at P from this. Okay. So it makes sense to subtract y at P from this. And now I divide by t and I let t tend to 0. This is defined to be, therefore, this will give me a vector at P. This vector is defined to be the Lie derivative of y with respect to x. So Lxy at the point P. Okay. Is the definition clear?
Yes, sir.
Yes, sir.
Okay. Now, what is this? This thing is nothing but this d phi tp inverse of y at phi of tp, y phi tp. This is the same as the pullback by phi t of y, right? The whole thing at the point P. Is this clear? Minus y at P. Yes?
Yes.
Yes, sir.
Right? This is the pullback of y by phi t. So what is this? This is nothing but ddt at t equal to 0 of the pullback phi t star y at P. Okay? Ddt at t equal to 0. Yeah.
Yes.
Okay. So this, notice this phi t star y at P, this is a curve in a fixed vector space, right? In the vector space TPN. Right? I'm taking the vector fields phi t star y. That's a one parameter family of vector fields, but I'm evaluating them at the same point P. So I'm getting vectors in the same tangent space. So I've got a curve in a tangent I've got a curve in a vector space that I can take its usual tangent vector, right? At time 0. Is this clear?
Yes.
Okay. All right. So now what is interesting about this Lie derivative? Well, notice that see, y is phi t related to y for all t. This is if and only if phi t star y equal to y for all t, right? Yes?
Yes.
Yes, sir.
Okay. And well, okay, let me do the implications one way. So, okay, all right. All right, let me. So, what do I want to do? Okay. Right. So, yeah, let me just do this cleanly. So, well, I have it here in the notes. Let me see. Yeah. So, oh, okay. All right. Okay, let me just follow the notes. It's neater. I'll just follow the notes. Sorry. So actually, this Lie derivative Lxy, this turns out to be nothing but the bracket of x and y. This turns out to be nothing but the bracket of x and y. Okay. So let's prove this. Let's prove this. So we have to show what? That both of these vector fields acting on a smooth function f, they give the same value, right? Remember, we have the correspondence between vector fields and derivations of C infinity m. So we just need to show that these two vector fields are the same as derivations of C infinity m, right? Okay, so let's take an f in C infinity m, and I want to look at Lxy applied to f. So that's going to be a limit of certain things, right? So let me look at the following function of two variables, phi of AB. This is y applied to f composed with phi minus a. So phi minus a, this is the flow of x, all right? And then I evaluate, so f composed with phi minus a, this is a function. And I'm applying y to this. Okay, I can apply y to this function. So I get a new function. Then that function I evaluate at phi b of p. Okay, so A, B here are small real numbers near 0. Okay. So this is well defined, all right. The flow is defined for small times, so this makes sense. P is fixed here. Okay. So let me look at this function of two variables. Okay. So then let's calculate its partial derivatives at the origin. So del phi del A at 0, 0. This is the limit A tends to 0. So I have to put B equal to 0, right? So when I put B equal to 0, this becomes identity. Phi 0 is identity. So this just becomes P. So this will become Y applied to F composed with phi minus A at P minus Y applied to F at P. Now Y is a linear operator. So this is the same as Y applied to F composed with phi minus A minus F, the whole thing divided by A. This whole thing at P, right? Is this clear? By linearity of Y, right? Yes? Are you there?
Yes, sir. Yes.
This is okay, right? Okay. Now
Yeah.
look at this. So F is a smooth function and phi is the flow of X. So F composed with phi minus A minus F, this divided by A, this is the derivative of F along the integral curve of minus X, right? This is the derivative of F along the integral curve of minus X. So this function here, this converges to minus X minus XF pointwise, this function inside, right? And you can also show not only does it converge pointwise, but it also converges in C1 norm on charts. Okay. So the first derivatives of this function converge to the first derivatives of minus XF. All right. You can show that as well. And now Y is a first order differential operator. So if you have functions which converge in C1, then Y of those converge also, right? Yes. So a first order differential operator is continuous with respect to the C1 norm, right? So if this
Yes.
converges in C1, then Y of this will converge to Y of the limit. So this converges to Y of minus XF at P. So this becomes minus YXF at P, all right? So this partial derivative, del phi del A at 0, 0, this is minus YXF at P. Now let's look at the other partial derivative. So del phi del B at 0, 0. So here I have to put A equal to 0. So inside I just get F, and then I'm looking at phi B at P. So I look at Y of phi B of P, and I differentiate that with respect to B. So this is the same as ddt at t equal to 0 of YF at phi t of P. And phi t of P is the integral curve of X. So this is just the derivative of YF in the direction of X at P. So this is X applied to YF at P. Yes? Okay. Now, how is this related to the Lie derivative? So if I look at Lxy applied to F at P, what is this going to be? So Lxy is ddt at t equal to 0 of d phi minus t at the point phi t of P applied to y at phi t of P, right? This tangent vector. Yes. This is the pullback of y by phi t right? Is
Yes,
this
sir.
clear?
Yes, sir.
Yes, sir.
Right? Okay. So this applied to F. Now, what is this? So what is the derivative of phi minus t applied to this tangent vector applied to F? It is this tangent vector y at phi t of P applied to the function F composed phi minus t by definition of the derivative of a function of a map, right? Yes?
Yes, sir. Yes.
Yes, sir.
Yes.
Okay. So you have to compose f with phi minus t. Now, what is this? Y at the point phi t of p applied to f composed with phi minus t. This is the same thing as y applied to the function f composed phi minus t. The whole thing evaluated at phi t of p, right?
Yes.
Okay. Now, what is this? This is nothing but my function phi evaluated along the diagonal. This is phi of t comma t, right? Look at my function phi again.
Yes.
Phi of was y applied to f composed with phi minus a at the point phi b of p, right? So what I'm getting here is phi of t comma t, and by the chain rule, ddt at t equal to 0 of this will be del phi del a at 0, 0 plus del phi del b at 0, 0, right? And the first term is minus yx f at p, and the second term is xy f at p. So when I add these two up, I get bracket xy f at p. Is this clear?
Yes, sir.
Okay, so that proves that the Lie derivative and the bracket acting on f are equal. So therefore, this is true for all f. So therefore, Lxy is equal to bracket xy. Okay. So now we can come to a more geometric interpretation of the bracket. We gave a purely algebraic definition, but geometrically, we'll see what the bracket means. So the bracket of x, so the following are equivalent now. The bracket of xy is 0. Y is phi t x related to y for all t. That means the flow of x sends y to y, okay, for all t. And third is the flows of x and y commute. So phi sy phi tx is equal to phi tx phi sy for all st. Okay, so what we can take away from this is that the bracket is 0 if and only if the flows commute. The flows of x and y commute. So let's prove this. So 1 implies 2. So suppose the bracket is 0. Then we want to show that y is phi tx related to y for all t. Okay. So y being phi tx related to y for all t is the same as showing that phi t star y is equal to y for all y, right? For all t, right? Yeah, phi t pulls back y to y.
Yes.
For all. So let's look at phi t star y at a point P, and let me differentiate this, right? I can differentiate this at the point P. So what will the derivative be? So ddt is the same as dds at s equal to 0 of phi t plus s star of y, right? And phi t plus s is the same as phi t composed with phi s. So, or phi s composed with phi t. So when I pull back is contravariant. So the pullback by phi s composed with phi t will be the same as phi t star composed with phi s star, right? So this will become dds at s equal to 0 of phi t star of phi s star of y at p. Is this clear?
Yes, sir.
Now, phi t star is a linear operator, right? This is a linear operator. So I can take it outside the derivative, right? This will become phi t star of dds at s equal to 0 of phi s star of y, and then evaluate at p. Does this make sense?
Yes, sir.
Right? But now what is the derivative inside? The derivative inside is just Lxy, right? By definition, dds at s equal to 0 of phi s star y. This is Lx.
Yes.
So what do I get? Therefore, I get phi t star of Lxy at P, but Lxy is bracket xy, which we're assuming is 0. So therefore, this becomes 0. Okay. So therefore, the derivative of phi t star y at P, this is 0 for all t. Therefore, this curve is constant in t. So that means phi t star y is equal to phi 0 star y. And phi 0 star y is just y, because phi 0 is identity. So therefore, phi t star y is y for all t. In other words, y is phi t related to y for all t. Okay? Yeah? Is
Yes,
this
sir.
Yes, sir.
Yes, yes.
okay? And now 2 implies 3 is what we did earlier, that if a map, if 2 vector fields are related by a map phi, then phi semi-conjugates the flow of one to the other.
Yes.
So here that will just mean that phi tx will semi-conjugate the flow of y to it, the flow of y. So in other words, that means that the 2 flows will commute, right? Okay, so 2 equivalent to 3, this follows from the earlier proposition that we had, that that equivalence of 1 and 2 here, right? Okay, so the equivalence of 1 and 2 here gives me the equivalence of 2 and 3 here. And well, 2 implies 1 is also, so 2 is equivalent to 3, 1 implies 2, and 2 implies 1 is trivial, because if y is phi t related to y for all t, then the bracket xy, this is the same as Lxy, this is the same as ddt at t equal to 0 of phi t star y. This is 0 because phi t star y is equal to y for all t, right? Is this okay?
Yes.
Okay, all right. Okay, so the upshot is that the flows of 2 vector fields commute if and only if their bracket is 0. So the bracket, therefore, should be measuring some sort of I mean, the failure to commute of two vector fields, right? The failures of the flows to commute. So let me actually give you a geometric interpretation of the bracket. So first, let me do this in Rn. Okay, what is the bracket of vector fields in Rn? So here it turns out you can get this in the following way. So I take a point P, okay. Then what I do is I flow along in the direction of X, okay. So I flow along for time t in the direction of X. Then I flow along in the direction of Y, again for time t. Then I flow in the direction of minus X for time t. And then I flow in the direction of minus Y for time t. Okay. Now, if the flows commuted, then this curve would close up to give me a quadrilateral, right? Yeah, if the flows commuted, yes?
Yes, so we'll be able to
Yes, sir.
complete the
Yes.
quadrilateral.
Yes.
Right. So if they commuted, then this would close up. Now, in the general case, they don't commute. So what happens? So let me call this point, say, P of t. Okay. Now, what is this distance between P and P of T? What is the order of this distance? Well, if I flow for time T, I move a distance which is big O of T, right? And then I move a distance again big O of T, and again a distance big O of T, and then a distance big O of T. So the distance between P and P of T, this is of course going to be therefore big O of T, right? Yes? But is that clear? Yeah.
Yes.
I mean,
Yes, sir.
it's at most of order T, but actually what happens is, because I'm flowing by X and minus X and by Y and minus Y, what happens is certain first order terms cancel. And what remains is that the distance between these is actually a smaller order. This is actually of order big O of T squared. This is actually of order big O of T squared. Okay. So it's a bit smaller than you would expect. That's because there's first order cancellation coming from going in the direction of X and minus X. All right. So that leads to a first order cancellation. What remains is a second order term. And so then what I can look at is I can look at the following limit, Pt minus P. Now, instead of dividing by T, I divide by T squared. And I take the limit as T tends to 0. All right. This turns out to equal the bracket at P. All right. So it's a limit of these small vectors where we don't close up. All right. The thing to keep in mind is you have to divide by T squared, not by T. Okay. If you divide it by T, then you would get 0. You wouldn't get anything meaningful. You have to divide by T squared. Okay. Is this all right? Yeah.
Yes, sir.
So this is the bracket in Rn. You can try and prove this. It's not too difficult. You can try and prove this. And this will tell us what to do in a manifold. So, well, I mean, in Rn, therefore, if I write instead of I put T squared equal to a variable S, right? Then what is my P of T? So I write it as a function of S instead of T. So in this case, what will I be doing? I will be flowing by phi. Okay, so yeah, so I flow backwards phi minus T Y phi minus T X. Okay, so let me remove this. So this phi T Y phi T X of P. So this is in terms of S, this is phi. So T is square root S, so minus square root S Y phi minus square root S X phi square root S Y phi square root S X of P. Okay. So this is so let me call this some Q of S. Okay. So this is a curve, right? Okay. This is a curve, okay. And so what I do is I can do this on a manifold, right? So here Q will be a curve from 0 epsilon into the manifold n if so xy belong to chi n. Okay. And Q0 is P. Okay. And here what I was looking at, this limit is the same as the limit s tends to 0, Q of s minus Q0 over s. Okay. So so this is nothing but Q prime 0, right? The tangent vector to this curve at time 0. So that's what I would do in a manifold. I define, so the bracket xy at P is nothing but the tangent vector to this curve at time 0, Q prime 0. So this is an element of TPM. Okay.
Yes.
Does this make sense? Yeah.
Yes, sir.
So this is a geometric interpretation of the bracket. Okay. Okay, so we just have 5 minutes left. I'm not going to start anything new. So any questions if you want to discuss anything? Maybe the bracket itself, yeah.
Oh, I mean, like at the beginning, I had asked you a question, and you were telling
Yeah.
that it depends on the curvature. So, like, I wanted to ask. My question is specifically in the setting of say compact Lie groups. So, in that case, like, all I want is that modulus of the Jacobian of the exponential map that to be bounded below by some positive real number. That will happen, or,
Sure, that is
that is going
right.
to be.
1 second, let me think a bit. Let me think a bit. Bounded below.
Yeah.
Oh,
That's
for
what
a
it,
compact group.
yeah.
Oh, no. Oh, that it can't be bounded below, right? Because the exponential map is mapping an infinite volume space, the tangent
No.
space.
I mean, like, I want to, if needed to, like, restrict on a smaller ball.
Yeah, I mean, restricted to a ball by compactness, it will be bounded below. Sure.
Yeah.
Restricted to a ball, it will be bounded below. It's just a positive continuous function, right? So it
Yeah,
will
so
not,
yeah, they need to go. Right.
just a positive, it's just the
Yeah, nothing.
determinant of the
Right.
derivative. It's just a positive continuous function. Yeah, there it's fine. Yeah.
But on the whole, it won't work, right?
No, right. Because if it's bounded below, then the image, like suppose it's bounded below by half, that means the image will have half the measure of the domain. Right?
Yeah.
But the measure of the domain is infinity. So then that means the image will also have measure
Yeah,
infinity.
because it's a compact Lie group. This Riemannian exponential.
No. Actually, wait. No, I'm making a mistake. That's not true. No. What I said is false. I mean, the map is not 1-to-1. Of course, it's not 1-to-1. It's a covering, right? It's more like a covering.
Yeah.
So yeah, no. In that case, no, it could be bounded below. I'm not sure. Yeah. Wait, let me think a second. It could be bounded below, in fact. Yeah. In fact. Like if I look at the exponential, let's say from C to C star, right? The complex exponential, e to the z, its derivative is just itself and the determinant is the mod of e to the z. No, that is not bounded below. No, that is not bounded below. The mod is e to the x. So yeah, for the complex exponential, the Jacobian is just e to the x, where x is the real part of z. So that goes to 0 as x goes to minus infinity. So there it's not true. No, there the Jacobian is not bounded below. Yeah, in general, I don't know. It may, it may or may not be bounded below. Yeah. Like if it's an abelian Lie group, then definitely yes. The exponential is a covering. And I mean, if it's a compact abelian, I mean, if it's a torus, if it's the exponential map of torus, there, yes, there it's very simple. In fact, there the Jacobian is constant equal to 1. So that's a trivial example.
As in the case of R and circle, the most baby case. Yeah. Right.
Yeah. Or for a torus, yeah, the Jacobian is constant equal to 1. But for a compact Lie group, let's say for SON, yeah, so for SON, I don't know. No, I don't know. I haven't thought about this yet. But at least on compacts, it'll be bounded below for sure. Yeah.
I mean, like restricting to a ball and that whole business goes through. That's what I'm saying.
Yeah. Restricted to a compact ball in the tangent space, it's true.
That's true, right?
Yeah, that's true.
But in case of, sir, what you're saying, in case of like compact Lie groups, we also have another advantage, right? Because it's a compact Lie group. It is
one second. The time is ending. If you want, we can just talk for another 2-3 minutes in another session.
Yeah, sure.
If you want to talk, you want to talk a bit more?
I just wanted to make a comment. I think 20 seconds is good enough. I just wanted to say that it's compact Lie group, so it's bi-invariant metric. So the Riemannian exponential and that will coincide. And in case of the Lie exponential, I think it is more tractable to compute the derivative. That's all.
Correct. That's true.
I'll think over it. Yes. Okay, sir.
Okay. All right. So